So in this particular lecture, I'm going to be showing all what I've already explained in the slides. So first of all, you need to install the PWR and ggplot2 package. If you don't have it, so try and install it. Then we load the packages. So this is currently an example. We are going to calculate the effect size from a pilot data. So the treatment mean is 120, the control mean is 130 millimeter mercury, and the pool standard deviation is 15. So what we're going to do is I've already given you the formula I told you earlier on. You subtract the treatment mean from the control mean divided by the pooled standard deviation. This is where you are going to calculate your coherence D. So we're going to run that now and see what we have. You can see we have minus 0.667, approximately minus 0.667. So if our coherence D is less than 0.3, so we are going to take the absolute value. So our coherence D now, you can see if it's less than 0.3, then the effect size is small. But if the coherence D is less than 0.7, then it is what? Medium. So we can see our coherence D is approximately equal to 0.7, because we're going to take the absolute value of this. So for relating to types of the errors and power, so you can see we have an alpha of 0.05, beta of 0.2. Then to calculate the power is going to be 1 minus beta. So when we run this now, once you have our value of beta is going to 0.8. So if you want to visualize the power with different sample size, first of all, we have to give our effect size. Then we'll give a random sequence of from 10 to 200 with a interval of 5. Then we now use the sapply function. From the sapply function, we're going to convert to a pwr.test t-test. This is a t-test we are using, where our n is equals to n. Each of this particular n that you see here, our d is going to be the effect size. Our significance level is going to be 0.05, and we are using a 2 sample t-test, and it's going to be also be a 2-sided t-test. So now we're now going to return the resulting power. So once we calculate this now, then we're going to check for the power values. You can see our power values in this place. Then we'll now create a power curve. So create a data frame from that particular power values and sample size, each sample size with its respective power values. So you can see each sample size with its respective power values. Now create a ggplot visualization based on this. So whereby we are giving our sample size as a x-axis and the power as the y-axis. So when we do that now, you can see we have this particular plot which you saw on this slide. So this is how you can do it. So now using the PWR package, I already showed you the PWR.t-test. So this is it. I told you the coherence D is the median effect size, and you get the coherence D either from previous literature, or you just subtract the two means from the both samples and divide by the pooled standard deviation. This is your significance level, your power. Then this is where you specify the type of t-test you are using, and it is also 2-sided or 1-sided. So you just run this now, and we will run the power analysis so you can see the power analysis. So for this particular values we have given, the number of samples that you need is what? 63 per group is 63 points. This is approximately 64. So 64 per group, you need 64 per group. So if you want to extract it, you can just use this particular n per group. This, so you can see it. This is 64. That's if you want to extract it. So this is for a t-test 2-sided. You can see it. And if you want to calculate the power now, we're using the same formula also now to calculate power. This time around, we're already given the sample. I told you need 3 to calculate the other one. So if we run these two also, power, this is 2. So you can see that what we get our power as approximately 0.7. So this is how you calculate your power. So calculate detectable effect for sample. So now this next one now also, if you want to calculate the effect size now, this time around calculating the effect size, providing power, significance level, and the samples. We'll run these two also. This is 3. So you can see the effect size now is going to be approximately 0.74. Now, you want to now calculate the power curve for multiple effect size. We have to give a sequence of the sample sizes. So 10 to 200 by 2. Then we have to give the effect sizes we are using that I'm interested in getting, that is 3. You can see the various effect sizes. and we'll have to calculate the power for all combinations. What we're now going to do is that we're going to create a for loop for each particular effect size. So for each effect size now, we're trying to calculate the resulting power. So the power, we're going to use the supply function on each of those particular sample sizes under each effect sizes. Then we apply the power formula for the t-test, and we get the resulting power for each particular combination of sample size and effect sizes. And we now return a data frame of the sample sizes, the power, and also the effect size. Then at the end, we bind our power curves with the what? This particular data frame we created to get the power curves data frame. So when we run all of this now, then we now run our ggplot2. You can see this is similar to what we have on the slide. Now, what of sensitivity analysis? So if the effect size is uncertain, this is the expected D. We want to calculate the sample size for the expected effect using the t-test now. You can see 2 sample. So our n expected is going to be what? You can see our n expected is well. So what if effect is smaller? Then what if the effect is larger? So what you're trying to see now here is different values of the D. So for smaller effects, what do we get? The value of the n is 64. While for larger effects, so larger effects usually have, so you can see for larger effects and the smaller effects are both the same. So smaller effects and larger effects are having the same value of what? N. We're trying to now calculate the power for this respective, for the same sample we get in this place, but for different effect sizes. You can see now that the power is 0.39 here, while the power here is 0.97. So this particular larger effect will be much better with this effect size 0.7. So this is sensitivity analysis. This is for independent sample to test to have our mean treatment, mean control, and the post standard deviation. And coherence D is usually your mean treatment minus your mean control divided by the post standard deviation. So this is now a two-sided test, as you are seeing. Just the same formula we used earlier on, only that we're changing the argument this time around. For the paired sample, this is still the same to the paired sample, but in terms of one-sided, you just change this alternative to greater than or less than if you are conducting a one-sided t-test. So if we just run all of this now, and we go to our value, independent one-sided, you can see independent one-sided now. You can see what we have. And if we check for independent two-sided, so you can see the n here. So you can see our power here. The n for the two independent one-sided was 50 per group, so two-sided is 63.7. So because the two-sided we are not sure of the direction, one-sided we are sure of the direction, so that's why the number of samples is less than the number of samples in the two-sided. So for this is for the paired sample t-test now. So the mean difference is 5. For blood pressure after measurement is standard deviation, post standard deviation is 8. So you divide 5 by 8, you get your coherence D, and you put it this time around, you put two-sided, you change the argument to paired instead of two sample t-test. So when you run this now, you can see, try to get our paired analysis. So you get 22.09. So this is going to be yourself. So the one thing with the paired sample t-test, it doesn't use much samples compared to the other type of t-test. So this is the one sample t-test now. Our hypothesized mean is 100, and your population mean is going to be 100. So your standard population is 15. So you can say 105 minus 100 divided by 15. And anything you have, you use it as your coherence D. You just change your type to one sample. Your alternative is two-sided. So when you run this now, you get your D1 sample. It's going to get 0.3. It's just one sample analysis. So you're going to be getting approximately 73 as your t-test power calculation. So now our sample size table for different effect sizes. So these are different effect sizes now. We're going to get the sample size table. I'll create a data frame with the columns effect size, the number of samples per group, and the total n. I'm going to create a for loop now, whereby we're applying each of these power tests while trying to for each of these effect sizes that we have. So we're going to try to get the number of samples, and that number of samples we put it in is our number per group column, and also the sample size, the total inside our sample, and the total n column. So let's just run this and see what we have. So you can see the total n here. So this is it, n number of per group. So the total n is usually this 394 times 2. So the total n is usually 394 times 2. That's how we got the total n. You can see what we did here, the number per group times 2. So if you want to account for attrition, I told you attrition is usually 20%. If you expect 20 expected dropout, so you add 20% on your sample size. So now recruited n, now we're going to be recruited n. So if your required n is 64 and we have 0.2 here as your attrition rate, so you have to add 20% more of your number per group. So when you run it here now, our recruited n, now if you look at this now, so recruited n is going to be what, 80, because 20% more than 64. So now this is a two proportion test. This is now for two proportion. I told that the two proportion, this is the calculation of the two proportion, this es.h function. So if we have proportion as 0.8, vaccination success rate, and the placebo is 0.6. So if you want to calculate your coherence n, you use this particular function, and you put this particular h value inside your pw.2p.test. This for proportion, and you run it. You can see for our two proportion analysis, we have our n is 80, approximately 80 numbers per group. So for the one proportion test, so this is an example whereby the local rate is 0.65 compared to the national rate of 0.7. You put it inside this es.h function to get your h, and you put your h inside the pw.p-test function. So once you run all of this, you should be able to get the number of samples you need one prop analysis. So what do you get is 687.8082. So approximately that's the number of samples you need per group. So this also is sample size for proportion test. Just like I did earlier on, we have a fixed baseline proportion. Our differences, these are various differences that we have, maybe comparing to various populations. So now creating a table now, as you can see, this particular table that we have now, we're going to be having 5 columns: the P1, P2, the difference, the coherence age, and the number per group for each of these combination of proportion and the differences. So we create a for loop now to get the coherence age for each combination above, and also we use the P proportion sample size calculation formula to get the number of samples for each combination, and also our coherence age, and then also the number per group. So when you run this now, you can see we have the P1, the P2, and the differences. You have the coherence age, you have the number per group. So you can look at it. So you also want to visualize this now. We can actually visualize this. We're just going to run this now. These are baseline proportion, a sequence from 0.1 to 0.9 with a interval of 0.1 and interval 0.1, and the difference is we have a fixed difference now, 0.15. So of course more or less like creating a data frame in this place for the particular combination upward that you're looking at. Then we have our baseline data here, and we have our ggplot2 function that we're trying to plot here. So you can see this is the sample size versus baseline proportion. So you can see the number of sample size needed per group at the baseline proportion. So you can see the highest sample size per group is around 0.4, and the lowest sample size around is before 0.2, and also we have 0.82, around 0.82 also. The baseline proportion around 0.8. You can see this for various baseline proportion, the amount of sample size that is needed. So we're trying to look for the minimum with the moderate baseline proportion. So this is also another data frame here now, also of the high baseline, low baseline, and mid baseline. We have various P1, various P2, and we're going to also be calculating our coherence each here, creating a data frame here. And this for loop is going to help us calculate the number of sample size needed for each combination above. And when we print this, you can now see that you have a bigger view of the table. So you can see for each scenario, the P1, the P2, high baseline. So you can see in this place we have a very high baseline. Here we have a low baseline. This is a low baseline here, the high baseline. And you can see the difference in this place. We have a fixed difference. This is the coherence age, and this is the number of per group needed. You can see it. So this I can calculate your sample sizes for both proportion and also test of proportion and means when time was called. So you can also check other formulas to also that are available for ANOVA for other statistical tests in calculating sample sizes.